Welcome to this explainer. You know, I am so incredibly excited you're here today because we're going to demystify something that honestly looks like pure magic, but, well, it's actually just brilliant physics. We're looking at the ultimate hero's toolkit, the mechanics behind how seemingly impossible heavy lifting gets done in the real world. I mean, from ancient construction all the way up to modern industrial might, the concepts we're exploring today are literally foundational to human progress. Let's get right into it. So I want you to start by picturing a massive ship engine, or, a giant block of solid stone. Now imagine trying to lift that massive object with just your own physical strength. Mentally feel the sheer difficulty of that, the absolute impossibility of that task. Your muscles would totally give out before the object even budged an inch, right? So the big question is, how do we do it? How did humans historically, and how do we still today, lift these multi-ton weights without always relying on massive, complex, modern hydraulics? Well, the answer introduces the ingenious hero of our explainer, the pulley system. Simply put, a pulley is a mechanical arrangement of wheels and ropes that distributes weight to effectively reduce the force required for lifting. It's an incredibly elegant solution. In fact, the ancient Greek mathematician Archimedes allegedly used a pulley system to drag an entire fully loaded warship by himself, literally just to prove a point to a king. By simply rerouting ropes around wheels, we completely change the rules of physics in our favor. Here is our roadmap for today. First up, the heavy lifting mystery. 2, the 3 basic types of pulleys. 3, the secret power, mechanical advantage. 4, applications of pulleys in industry. And finally, number 5, your guide to choosing the right pulley. Okay, section 1, the heavy lifting mystery. Let's talk about beating gravity. Moving right along to section 2, the 3 basic types of pulleys and escalating complexity. All right, let's start with the fixed pulley. This one is firmly attached to another object, like a ceiling or a heavy beam, meaning its position cannot be changed. The absolutely crucial point here is that with a fixed pulley, the tangential tension on the rope exactly equals the weight of the object itself. So you aren't actually reducing the amount of effort needed to lift the object at all. You're really just changing the direction of the force. You pull down to lift the weight up, which, hey, is definitely easier on your back, but you're still pulling the full weight. Now, the mechanics shift completely when we use a loose or movable pulley. Here, the pulley isn't anchored to a ceiling. It's attached directly to the load and actually moves with the rope. Because the rope goes down through the pulley and back up, the load is supported by 2 sections of the rope. This is a game changer. It effectively means the required tension equals just half of the object's total weight. Sure, you have to pull the rope twice as far, but it feels exactly half as heavy. And by combining the fixed and loose pulleys together, we hit the next evolution. You really get the best of both worlds here. You get the directional advantage of the fixed pulley, meaning you can stand comfortably on the ground and pull downwards, while also getting the incredible weight-having advantage of the loose pulley moving with the load. We're starting to distribute the physical load further and further out. This all builds into the ultimate lifter, the compound pulley. A compound pulley is a full integrated system of multiple fixed and moving parts. The sheer genius of this system is that the weight of the object is distributed across the total number of ropes used in the system. Add more ropes and wheels, and the fraction of the weight you actually have to pull just keeps dropping and dropping. Section 3, the secret of power, mechanical advantage. Imagine strapping your hands to a 100-kilogram load that's over 220 pounds. Visualize the immense, back-breaking force it would take to try and deadlift this naturally straight off the ground. I mean, for most people, that's just totally impossible. But if we apply mechanical advantage and support that exact same 100-kilogram load with just 2 parts of a rope, like in our movable pulleys example earlier, the math changes completely. You only need to apply 500 newtons of force to lift it. By distributing the load across multiple segments of rope, the mechanical advantage literally halves the physical struggle. You've suddenly gained superhuman strength just by some clever routing of a cable. How cool is that? The numbers prove this perfectly. Let's say we keep a constant load of 100 kilograms. A fixed pulley still requires 100 kilograms of tension, but add a loose pulley into the mix, and that tension gets sliced right in half. In a compound system, the tension drops to its absolute lowest, perfectly distributed across the entire setup. The math unequivocally proves how the required pulling force just drops dramatically as the system becomes more compound. Okay, section 4, applications of pulleys in industry. Let's look at this on a massive global scale. These principles we've been talking about, they are the standard mechanics for the biggest jobs on Earth. We're talking about massive overhead cranes in warehouses, complex ship rigging out on the high seas, and heavy-duty engine lifting in automotive and aerospace manufacturing. But using these highly compounded systems, a single human operator or even just a relatively small electric motor can effortlessly lift materials weighing several tons. It's wild to think about. But here's the thing, pulleys aren't just for lifting. This stepped pulley is an absolutely ingenious variation. Instead of separate wheels floating around, a stepped pulley features multiple pulleys of different diameters all stacked together on a single rotating shaft. It kind of looks like a staircase. And its purpose isn't to hoist heavy loads, but to fine-tune the inner workings of heavy machinery. Stepped pulleys act a lot like mechanical gearboxes. They control speed and torque, and they are completely standard in workshop equipment, things like drill presses, lathes, and milling machines. By simply shifting a drive belt from a larger step to a smaller step, a worker can instantly change the rotational speed of a drill. And that is absolutely vital, because you need a vastly different speed to drill through softwood compared to hardened steel. Best of all, this simple, brilliant mechanical design replaces the need for highly expensive and delicate electronic speed controllers. Section 5. Your guide to choosing the right pulley. Let's talk practical application. If you're building a system, here are your punchy manufacturing standard steps. First, material matters. Always choose steel for heavy loads and harsh environments because it totally resists wear. Second, geometry matters. Select a larger diameter wheel whenever you possibly can. A larger wheel means the cable doesn't have to bend as sharply, which drastically increases the lifespan of your rope or wire. And third, for the internal bearings, opt for bronze bushings to guarantee true industrial durability. Choosing the right materials doesn't just ensure efficiency, it ensures the long-term survival of your equipment. And look, we absolutely cannot talk about heavy loads without highlighting this crucial safety feature. When you're managing multi-ton vertical ascents and descents, extreme reliability is non-negotiable to prevent absolute disasters. That's exactly why modern industrial setups integrate motion arrest devices. These safety mechanisms instantly lock and manage the loads to prevent accidental slipping if a rope drops or an operator accidentally lets go. Safety always has to scale up right alongside your mechanical advantage. To bring this whole thing together, I want you to remember this golden rule. Every time you add a supporting rope part, you decrease the required force. That right there is the essence of mechanical advantage. It's simple, it's elegant, and it literally shaped the built world around us. So, I'll leave you with this. If a few simple ropes and cleverly arranged wheels can empower a single person to lift literal tons, what other seemingly impossible limits in our lives or our industries can we break simply by rearranging the tools we already have right in front of us? The physics of mechanics isn't just about moving heavy objects, it's a blueprint for human ingenuity.